A box of mass m1 is 2.1 kilograms and is being pulled by a horizontal string with tension T as shown above. It moves to the left with a constant velocity. Across the top of the second box, having a mass of m2 of 5.1 kilograms, kinetic coefficient of friction between the upper box and the lower box is 0.6. There's no friction between the lower box and the horizontal floor, and the lower box accelerates to the left. Assume that the upper box is moving faster than the lower one. Okay, moving faster than the lower one, which seems kind of implied, though I'm glad they said it explicitly, by coefficient of friction being kinetic as opposed to static. Basically, you have different coefficient of frictions if there's relative motion between the surfaces or not. Okay, which of the following statements best describes the net force of the upper box? Okay, so the upper box is moving with a constant velocity. So sum of all forces equals mass times acceleration, total, net. And therefore, if it's moving with a constant velocity, you can see this from the kinematic equation. V equals AT plus V naught. X equals 1/2 AT squared plus V naught T plus X naught. Where if you have, looking at the second equation here, if V naught and V initial are the same, then your acceleration has to be 0. So a constant velocity implies a 0 acceleration, which implies net force is 0. So which of the following best describes the net force acting on the upper box? And that is 0. 0 net force. Because 0 acceleration, which is implied by constant velocity. Which of the following statements best describes the force of friction acting on the lower box? Okay. So we have force friction from the upper box acting this way. It's opposing motion. This is actually the dots in the same spot. I'm just drawing it below so you can see it. We have a force of friction operating to the left, left, on the lower box. And a couple ways of thinking about that is we have the force going this direction from the top one, and to oppose that, we're going to need to have a force on the bottom going to the left. Another way to do that is we normally choose a static reference frame, basically when we're looking at it from like an observer watching it from the outside. But that's not necessarily true. We could actually be moving. So there's a general rule of thumb that force of friction opposes motion. So if our point of view, if our reference frame was following M1, basically moving along with frame 1, so it looked like frame 1 was stationary, then the relative motion, since it's moving faster than M2, it would look as if M2 was moving to the right. And that movement to the right would be kind of like, well, okay, moving to the right relative to M1, and that would cause the force of friction to oppose the direction of motion, which would be to the left. So there's two ways of thinking about it. One, you can look at the force of friction that's opposing the motion of M1, and then to counterbalance that, you're going to need force of friction M2 going to the left. Basically, each action has an equal and opposite reaction. The other way of looking at it is you can make your reference frame M1, and then it looks as if M2 would be moving towards the right, and then the force of friction would be opposing direction of motion. Either way, you get the, which best describes the force of friction acting on the lower box. The force of friction will be pointing to the left. Okay, what is the magnitude of acceleration of the lower box? Okay, so the idea here is you have a constant velocity here, and this is pulling the mass, due to friction, of M2 along with it. So the mass 2 is going to be accelerating. So we have constant V, constant velocity. This will not be constant velocity. This is actually accelerating. And so what we're going to do is we're going to say something along the lines of, well, the force that's doing the acceleration, so the net force, which is always going to be mass times acceleration, is going to be the same as the force to the friction in magnitude. So it'll be opposite direction, but it'll be equal to the force of friction from the top box. And force of friction is normal force times coefficient of friction. That's just something you should have memorized. And it's kind of mostly true. It's an approximation. Normal force will be mass times gravity times mu k, and this will be mass of 1. And so if we look at this one, we look at that one, this is actually mass 2 right there that's being accelerating. So we have acceleration equals mass 1, gravity, mu k, over mass 2, which is, I'm going to have to look at some of these numbers. So we have 2.1 and 5.1. So 2.1 times 9.81, which is gravity, times mu of k, which is 0.6, all over 5.1. And so, get the calculator on clear. 2.1 times 9.81 times 0.6 divided by 5.1. That gives us 2.424 meters per second squared, because it's an acceleration. So we come back over here, 2.4. That's close enough. So I will call B the answer there. Right. So we kind of look back what happened, and see what we did. So we had two boxes, one moving on top of the other. This is moving at constant velocity. This is moving. M2 is moving at initially a slower. Actually, I'm going to say at initially a slower velocity, but it's now accelerating along with M1 due to friction. And this friction is caused by a normal force and a coefficient of friction, mu k, from M1. And it's moving along a frictionless plane. We look at all that, and we kind of analyze where the friction forces are and what it's doing. And then we're asked to find out what's the acceleration of the lower box. And the acceleration is all due to the force of friction. And we know that force equals ma. Using those two ideas, we put them together, jumble them up with some algebra, and then when we finally solve it, we got an answer of 2.4 meters per second squared. So I hope that helped. I will see you next time.